outline of my talk. Firstly, I talk about overview of supercake B and final focus system, and next magnet design, and cryostat and cooling system, and magnetic measurement, and finally I summarize my talk. This is a picture of the supercake B area, and this is Mount Tsukuba. And supercake B is a high-energy electron-positron collider, and it's already construction finished at KK. And this is improvement to machine of KKB accelerator. And supercake B is aiming at a high luminosity of 8 times 10 to 35th square inverse square and time inverse second. This is 40 times larger than KKB. And this is a main parameter of the supercake B. Beam energy is 4 GeV for positron beamline and 7 GeV for electron beam. And they collide with a large crossing angle of 83 milliradian. And they are focused at interaction point. This is a vertical beam size at the interaction point, and the for positron beam, and the size is 48 nanometer and 62 nanometer for electron beam. This is a schedule of our supercake B. Phase 1 was finished on the June 2016. This is operated without final focus system and without filter detector. And phase 2 is started from this February will be finished this July. And this machine, this is operated with final focus system and with filter detector, but no vertex detector. And phase 3 will be start 2019 with full filter detector, and physics run will be start. Now we are here. Next, I will talk about QCS. Final focus. QCS is means final focus superconducting quadrupole system on supercake B. This is a construction history of the QCS, and the construction of the real magnet began at June 2013, and construction of QCS has been completed and installed into the beamline on February 2017. And we have magnetic measurement at the beamline from June to August 2017, and installation of beam pipes and connection with QCS and belt was completed on this June. And beam operation started on sorry, this is mistake. Beam operation started on March 2018, and the first collision was observed to April 2018. And this is a final focus system of supercake B. And QCS consists of 4 quadrupole magnets for each beam line. And this figure showing that this blue line is electron beam line, and the red line is a positron beam line. And this square showing the magnet, quadrupole magnet. And they have 43 conductor and cancel coil. And this final focus system is located in the large detector solenoid, and they have 4 compensation solenoid to compensate L2 solenoid field like this. This is a drawing of the QCS and L2 detector. And here is the main parameter of the QCS quadrupole. In this column showing the field gradient, and this column is current, and this is inner radius, and this is a effective length. For QC1LP, the magnet field gradient is 68.94 Tesla per meter, and operation current is 1,625 ampere, and inner radius is 25 millimeter, and magnetic effective length is 3,034. And the other magnet is like this. And this is we have 4 types of cross-section quadrupole magnet. So they are different in the diameter. Also, this is a quadrupole magnet. This is a drawing of the quadrupole coil, and this is a cross-section of the quadrupole magnet, and the quadrupole magnetic field is generated by cosine 2 theta winding and double pancake winding. We use Rutherford cave, and the cross-section is here. It has a keystone angle of 2.6 degrees. They are made of niobium titanium. This is a cross-section of QC1LE with liquid helium vessel. This circle is a electron beam line, and this circle is positron beam line, and this red circle showing the main quadrupole conductor, and green one is color, and blue one is permanent yoke, and this is a permanent also permanent yoke, and the large circle of red circle is QC ESL compensation solenoid, and purple circle is a tungsten radiation shield, and this outside circle is a liquid helium vessel. And next, collector magnets. One quadrupole magnet has 4 types of multipole collectors. Types of multipole of collector is B1, A1, A2, A3, B3, B4. And the wire, we use a niobium titanium wire, and the diameter is 0.35 millimeter. And the wire is wound by direct winding method. And this coil magnet is produced by BNL under the US-Japan research collaboration. And the collector and main quadrupole was independently wound, and there is a small gap between collectors and main quadrupole to avoid unwanted stress to the collectors. Yes, 4 types of this is a collector picture of the collector. 4 types of collectors are wound at one bobbin, and collector are inserted in. This is a main quadrupole. So this collector are inserted in a side of main quadrupole magnet like this, and the low angle and between collector and main quadrupole is fixed with keys equipped on the collector bobbin. This is a collector bobbin, and this is a quadrupole, and here is a key. And this is a typical measure the profile of the collector. And this is for the B1 collector of Q6LE. Left plot is B1 main component as a function of actual position. And this is a sextupole component, and this is a decapole component. Blue one is a normal component, and the red one is a skew component. This profile satisfies beam optics requirement. And next, cancel coil. Cancel magnet cancel a weak field from the main quadrupole magnet on the positron beam line to the electron beam line. Cancel magnet consists of B3 magnet and B4 magnet, B5 magnet, B6 magnet on each side. And this is a layout of cancel magnet, and this is a positron beam line, and this is a electron beam line. Here is a QC1LP, and this is a cancel magnet. This is a picture of the cancel magnet. Here is a cancel magnet. This is a collector for the QC1LP. This is a field profile of the B3 cancel coil and canceled field on the electron beam line. Upper plot showing the cancel B3 profile as a function of actual distance. You can see that like sextupole field is generated by the cancel B3 magnet, and this is when we turn on the QC1LP, the sextupole component is cancelled. This is our side of the another side of the cancel coil, also cancel. And next, compensation solenoid. The compensation solenoid generates inverse field with respect to belt solenoid field, and the integral field along the beam line becomes zero. So this is a plot of the profile of the solenoid field. Red line showing the BZ field for the just only the bell solenoid, and the black line showing the bell solenoid and compensation solenoid field. You can see that compensation field may generate cancelling field. This is a 3D model of the compensation solenoid. This is ESL, this is ESR1, and this is ESR23. And this is a magnetic yoke for the QCS. This is also magnetic yoke for the QCS. And ESL consists of 12 coil blocks, and ESR1 consists of 50 coil blocks. And ESR23 consists of one solenoid on each beam line. This is a parameter of compensation solenoids. For ESR1, the nominal current, operating current is 450 ampere, and stored energy is 244 kilojoule, and inductance is 9 Henry, and maximum field in the coil is 3.2 Tesla, and the load line ratio is 0.51. This is a picture of the ESL and the ESR1. And this is a current protection system, and we are using our tolerance is for the voltage is less than 200 volt, and temperature at quench less than 200 Kelvin. And so to do that, we use a diode protection. And this is a for quench result from the quench test. This is as a as a function. This is a voltage profile as a function of time, and voltage is 140 volt, and this is temperature. Temperature is about 50 Kelvin. So this is this system is working well. And so interesting feature of the ESL ESR1 is variation of inductance. If the current of ESR is reduced, the B field of belt 2 is flown into the QCS yoke. The permeability is saturated. As a result, the inductance of ESL ESR exhibit large variation. This is a calculation result of the inductance for ESR1 as a function of current. You can see that blue line is inductance. Blue line is rapidly increasing from 350 to 400, from 0.2 to 1 Henry. ESR1 is increased from 1 to 7 Henry. So this behavior makes it difficult to design power supply of ESL ESR1 so that the power supplies do not oscillate during energizing the solenoid. And this is a picture of the quadrupole magnet. And this assembling like this. And this is for quadrupole magnet, and this is iron is assembled, and support is assembled, and here the ESL is assembled, and here assembling the Lagrange field of tungsten alloy on the ESL, and covering the cold mass with the helium vessel and welding the cross vessel. And this is QCS at IR without bell 2 detector. And this is a QCS and bell 2 detector before closing concrete shield. This is a QCS-R, and this is QCS-L. This is bell yoke. Next, cryostat and cooling system. Cryostat is made. We have two cryostat, and inside the cryostat we have a beam pipe with room temperature and permanent jewel, iron yoke, and tungsten shield and support, and long and slim coiling channel for pipe. And helium vessel. This is a helium vessel. Helium vessels are fixed to the vacuum chamber with titanium 6 aluminum for vanadium rod. This is a support rod. So the total cold mass for the QCS-L is 1,522 kilogram, and for QCS-R 3 tons. And this is a service cryostat. And we have two refrigerator. Each cryostat has individual cold box with a cooling power of 25 watt. The cold box has served for the Tristan and KKB project for about 30 years. And this is a cool down profile of QCS-L, QCS-R system. This is a QCS-L, and the cool down time is 44 hours. For QCS-R, the cool down time is 55 hours. Okay, next I will talk about magnetic measurement. We have performed the magnetic measurement at the beam line for the field quality of the quadrupole magnet and collector canceling magnet is performed by using harmonic coils, and profile of solenoid coil was measured by using Hall probe, and magnet center was performed by single thread wire method. Yeah. First, I talk about harmonic coil system. This is our harmonic coil system consists of long coil to measure the integral field and short coil to measure field profile. This is this is a figure for our measurement system. Harmonic coil is here. And this is a measurement result for the higher order harmonics of the quadrupole magnet. These 8 plot showing the eight quadrupole magnet as a of the amplitude of harmonics as a function of harmonics order. You can, our tolerance is for sextupole component should be less than 10 units. For octupole component less than 5 units. This can be corrected by using the collector magnet, and the other component less than 1 unit. So this is a QC1 LP and QC1 RP and QC1 LE, QC1 RE. For the this magnet, the multiple amplitude are less than 1 unit, and for QC2 L and QC2 LP, RP, and QC2 LE have a few units for the several components, but this is not so large impact for the beam optics. And so QC2L, but QC2 RE shows a large amplitude for sextupole and octupole. And this is a typical profile of quadrupole magnet. This is a QC1 LE, and this is a main quadrupole component, and red line showing calculation, and blue line showing the measurement result. And this is a octupole component, and this is a dodecapole component, and this is a sextupole component. All profile is a very small error field. And for the QC2 RE profiles, we have large error field. This is a QC2 RE profile for main component, and this is a sextupole component, and this is an octupole component, and this is a dodecapole component. This is a yoke of the QC2 RE. So you can see that at yoke end, large error field. So this is showing the, so black one is a calculation result. So black ones do not showing the error field, do not showing the error field. So this calculation performed without solenoid field. So this is caused by solenoid field which flowing into the yoke end. But this profile also currently no problem for the optics, beam optics simulation. Okay, sorry, this is mistakes. So next, we will perform the single solid wire measurement. This purpose is a measurement of the magnet center of quadrupole magnet. And this is performed under collaboration between the Ferrominas laboratory. And this is set up for the single thread wire. This is QCS system, and this is a single thread wire unit, and the wire is from here to here, it's strained. Wire length is 9 meters. So this is the result of the magnet center for each magnet with respect to beam line. Upper plot showing the horizontal center of the quadrupole center, and lower plot showing the vertical offset of the quadrupole center, and red plot showing the measurement performed under the belt solenoid, and compensation solenoid is on, and black one showing the belt solenoid and compensation solenoid is off or off. And you can see the magnet position are varied with the solenoid field turned on and off. For X direction, about 0.1 millimeter. For Y direction, 0.3 millimeter. And the left plot showing the electron beam line magnet for QC1, QC2RE, QC1LE, QC1RE, QC2RE. Right plot showing the positron beam line magnet for QC2LP, QC1LP, QC1RP, QC2RP. So that maximum offset from the beam line are 0.5 millimeter for QC1RP in X direction here. And the maximum offset from beam line are minus 0.6 millimeter for QC2LP in Y direction. Here, and these offset can be corrected with dipole correctors. And I will summarize this talk. Super KQB starts operating with final focus system on March 2018. QCS construction began at June 2013 and completed on February 2017. QCS is a complex superconducting magnet system and consists of 8 quadrupole magnets, 43 collector and cancel magnet, and 4 compensation solenoids. And cool down was successful. The time from room temperature to 4 Kelvin is for QCS-L it's 44 hours. For QCS-R, 55 hours. Field quality of main quadrupole satisfy requirement from the optics simulation. Alignment of the quadrupole center was confirmed with single-threaded wire method. And QCS system is in operating and is now stable. And some quenches was happened by beam injection tuning. So quench detection system also working well. That's it.
Thank you very much. Do we have questions for Yasushi? Yes, Michael.
I have 2 questions. The first is on the unexpected profile of QC2RE, where you show that there's like 100 units.
Yes.
So can you tell me again, so this is due to the fact that on one end it's close, they sit closer together and the ion is not enough to provide the isolation needed. And is this a problem, the 100 units there?
This quadrupole is far away from the IP. So this is not so problem due to the optics group.
Okay, it's not a problem from the optics. And the second question has to do with you took a lot of time to measure the magnetic center of all your elements. Mm-hmm. And I was surprised to see that your average, you're off by 0.5 millimeters, by 500 microns. Is this surprising? I think this is a bit big, isn't it?
Sorry?
The maximum offset from beam line is 0.7 millimeters.
Yeah.
Is that what you expected? Isn't that a bit too big?
A little bit big, but little big, but so our alignment, our alignment stage is very difficult to the very big alignment stage. So it is difficult to tune the fine tuning is very difficult. So this precision is not so big, but big, but so big.
Okay, maybe just one urgent question because we're running a bit late. If not, let's thank the speaker again.